Okay, this is A2Further, and we're looking at first order differential equations. First of all, exact ones. So consider the first order differential equation. Here it isn't possible to separate out the variables, so that wee bit previously, and just from regular A2 maths, we would get all the x's on the x to one side and all the y's to y to the other side. You can't do that in this particular case. But the left hand side is x, y squared differentiated, which make it an exact equation which can be dealt with in the following way. 2xy dy by dx plus y squared is e to the 2x. Note the implicit differentiation. If you differentiate x, y squared, so we got to use a product rule here. So that there would be your u, and that would be the v. So this is going to be u dv by dx. So it's x times d by dx of y squared times v du by dx. So u dv by dx is going to be, if we leap down here, it's going to give us then it's going to give us x upon 2y dy by dx, and then plus y squared then times by the 1. So we have 2xy dy by dx plus y squared. That means if you integrate this, you just end up then with this. So the integral of 2xy dy by dx plus y squared dx equals xy squared. So it just makes this a very straightforward one in the end, and it's a question of spotting that that's going to be this, xy squared, then differentiated. So integrating this side becomes xy squared, integrating this side of course becomes a half e to the 2x. This is a general solution. A particular solution may be obtained if further information is given. Thus, one side is the exact derivative of a product and the other side can be integrated relatively easily using the above method. So let's take a wee look then at this one. So if a first order differential equation is not exact, then we can make it so by multiplying each side by an integrating factor. So example 1 is x, y dy by dx plus y squared equals 3x. If we consider the one we were looking at last time, so if you differentiate x, y squared, what do you get? You get u dv by dx. So that would give me, let me see to get this the right way around, 2x y dy by dx plus v du by dx, differentiating the x, then it's just going to be a y squared. So that's quite like that, only there's a 2 there unfortunately. But if we actually look, instead of this being differentiated, what about if we differentiate this? X squared, y squared. So u dv by dx is going to give me 2x squared y dy by dx plus v du by dx. So it's then going to be 2x y squared. If we look at this, if you multiply this by 2x, you will end up with this. So therefore, this has an integrating factor then of 2x. So if we multiply this by 2x, which is known then as our integrating factor, we will get 2 times by 2x, which is our integrating factor. That gives me 2x squared y dy by dx plus 2x y squared, and times obviously this side as well will give us then 6x squared. So how does that help? That means we've turned the left hand side into an exact differentiation. So if we integrate both sides, the integral then of 2x squared y dy by dx plus 2x y squared equals the integral of 6x squared dx. This just becomes x squared y squared, and this then becomes 2x cubed plus c. And that's effectively the secret to doing our first order differential equations. We are not quite there with them yet, but it's all about finding your integrating factor now with a different way, because it's a bit of a guessing game the way we worked our way through that. as to work it out. However, there is a better way then of working that out, and we'll be able to check that out then in the next video.